as we have derived earlier, the molecular flux for a binary system, which can be written as Na is equal to minus dAb dCa by dZ plus Ca by C into Na plus Nb. We can now write this above equation in terms of molar fraction, which is Xa is equal to Ca by C, or Ca is equal to C into Xa. Now substituting or putting the above equation into the term of Na, we get Na is equal to minus dAb C into dou Xa by dou Z plus Xa into Na plus Nb. So the Na term is the combined flux or molar flux. The minus dAb into C into dou Xa by dou Z is the molecular flux, and Xa into Na plus Nb is convective flux. Now, since the concentration of A is very small and the liquid layer of B is stagnant, we can assume the convective flux term to be 0 and we can neglect it. So, we can write Na is equal to minus dAb into C into dXA by dZ. This becomes our combined flux or molar flux term. So, now we will write the objective of the given problem. The first objective will be finding the concentration profile of A. The second objective will be finding the average concentration of A in the liquid phase. The third objective will be finding the rate of consumption of A. And the fourth and final objective is finding the flux profile of A. So, to achieve the above objective of the given question, we need shell mass balance on the system. Firstly, we need to select an appropriate system applying the law of conservation of mass of species A in binary system over the volume of the shell. So, the mass balance can be written as rate of mass of A in minus rate of mass of A out plus rate of production of mass of A by homogeneous reaction, since it's mentioned in the question that it is an irreversible and homogeneous chemical reaction. The conservation statement can be expressed in terms of moles. The chemical species A may enter or leave the system by diffusion, that is, by molecular motion and also by virtue of the overall motion of the fluid, that is by convection. As we saw in the term of Na, that we have two terms. One is the molecular flux and the other was convective flux. So we can say that the chemical species A may enter or leave the system by diffusion, that will be the molecular flux or motion, and the overall motion of the fluid, that is by the convective flux or motion. So both of these being included in Na. Also, in addition, the species A may be produced or consumed due to the homogeneous chemical reaction. In the given binary system, we need to apply a shell balance of finite thickness This is the finite thickness of delta Z, and then we consider this thickness to be infinitesimally small. So as a result of this process, there is a differential equation for the mass or molar flux is generated. If into this equation we substitute the expression for the mass or molar flux in terms of the concentration gradient, we get a differential equation for concentration. So as we have seen that everything is in terms of mass. So if we can convert it into concentration, then we might receive a shell balance equation in terms of concentration. Now, when we will have the shell mass balance equation, the differential equation can be integrated, and after finding out the constants of integration, we have to apply the boundary conditions. After applying the boundary conditions, we will come to an answer which gives us the concentration profile of A, the average concentration of A, and the rate of consumption of A. To first solve the differential equations, we will require to use some boundary conditions. And there are 4 boundary conditions which we can use as per mentioned in the question. So the first boundary condition can be the concentration at a surface can be specified. That is, XA is equal to XA naught. Like in the given figure or the given diagram, we saw a gas A and liquid B. Let us assume this is the origin where Z is equal to 0 and here Z is equal to L. So as per the first mentioned boundary condition, at the surface here the concentration can be Ca is equal to Ca naught or Xa is equal to Xa naught. The second boundary condition can be mass flux can be specified of a surface. That is, NaZ is equal to Na0. As mentioned earlier, here in the first boundary condition, the concentration at a surface was given. Similarly, in the second boundary condition, the mass flux of a surface can be specified. So here, for suppose NaZ can be written as Na0. The third boundary condition can be if the diffusion is occurring in a solid, it may happen that the solid surface that is of substance A is lost to the surrounding. Stream according to the relation Na0 is equal to Kc into Ca0 minus Cab. Here Na0 is the molar flux at surface, Ca0 is the surface concentration, Cab is the concentration in bulk fluid, and Kc is the proportionality constant. Also called the mass transfer coefficient. The final and the last boundary condition can be the rate of chemical reaction at surface can be specified. For example, if there is a first order chemical reaction occurring, then Na0 is equal to K1 double prime Ca0. That is, the rate of disappearance at a surface is proportional to the surface concentration, and K1 double prime is the proportionality constant. So, after having a discussion about the four boundary conditions, we now move towards achieving the objectives of the given problem. And the objectives were determining the concentration profile of A, the average concentration of A in liquid phase, rate of consumption of A, and determining the flux profile of A. So, the given system was of a beaker where we had a gas A and a liquid layer B. The gas A was diffusing into the liquid layer B, which was stagnant, and the A gas diffuses isothermally into the liquid phase. As A diffuses, it undergoes an irreversible first order homogeneous reaction. An example of such a system can be absorption of CO2 by a concentrated aqueous solution of NaOH. Now, as we can see, there might be some formation of AB component, but Using the pseudo-binary assumption, we neglect or ignore the small amount of AB which might have been formed. Hence, our solution, our binary solution, contains only A and B because we have neglected the AB component. Now, as we saw earlier, the shell mass balance, we can again write it as rate of mass of A in minus rate of mass of A out plus rate of production of A due to homogeneous reaction, which is equal to 0. So, first of all, we need to decide the direction in which diffusion occurs. That is, the direction in which the concentration varies. So, as we have seen that diffusion is basically the movement of molecules from a higher concentration to a lower concentration due to a gradient, we have to figure out the direction in which the concentration varies. That is, from a higher to a lower concentration level. So now, as we have seen in the problem, or as it is given in the problem, we are dealing with a problem of mass transfer, which means that concentration will be a driving force. And as we all know that concentration is a scalar quantity. Concentration, it is a scalar quantity. So, just because it is a scalar quantity, we do not have to worry about the direction. The direction in which the concentration varies. But unlike the problems that we have solved in class, which were momentum balance or momentum shell balance problems, over there, our driving force was velocity. And as we all know, velocity is a vector quantity. So, just because it is a vector quantity, we have to keep in mind the directions. So, one thing which we were doing in class, that is keeping in mind the directions in which the velocity might vary, we are not doing it over here because concentration is a scalar quantity. So, in class, as we were doing the momentum balance problems, the velocity had to be kept in mind and its directions. Suppose we had a Cartesian coordinate system, so all the three directions x, y and z had to be kept in mind, and we were checking with each and every direction. So here, just because concentration is a scalar quantity, we do not have to do that, and our problem becomes quite complexity free and it simplifies because the factor of direction is not included. So we can easily apply the boundary conditions which we have already discussed earlier, the 4 boundary conditions, and we can solve our differential equations and reach to the result very easily and hassle free. So, we only consider one direction here. To simplify our problem further, we assume that the concentration in our problem, that is of a gas A diffusing into the liquid B layer, occurs in one direction, that is in Z direction. So, all our calculations will be done taking into consideration this direction, that is the Z direction. So, for example, earlier, like we had written the molar flux equation to be as Na is equal to minus dAb into dCa by dZ. Or if we write it in terms of molar fraction, Na is equal to minus dAb into C into dXa by dZ. Here, after applying the direction of Z, we can write the above equations as NaZ is equal to minus dAb into dCa Z by dZ, or Na is equal to minus dAb C dXa by dZ. So, this is nothing but the molar flux or combined flux in Z direction, where our diffusion is occurring. Okay, so now let's move ahead and draw our system again of the glass beaker. As we have already seen earlier, we have a gas A and a liquid B, which is a stagnant liquid B, and the gas is diffusing into the liquid layer of B. Now, we will take a shell of infinitesimally small thickness delta Z. This thickness that we have assumed is delta Z. Now, taking into consideration this small thickness of delta Z, we now check the rate of mass flowing into and flowing out of this thickness. Let us assume that the rate flowing into the shell of thickness delta Z is NaZ at Z is equal to 0, because this is Z is equal to 0 and this is Z is equal to Z plus delta Z. So this NaZ at Z is equal to 0 is the rate of mass flowing into the shell of thickness delta Z, and that the rate of mass flowing out of the shell of thickness delta Z is NaZ Z plus delta Z. Also, the surface area of the small shell of thickness delta Z is assumed to be S. So, as we saw earlier, NaZ at Z is equal to 0 and NaZ at Z at Z plus delta Z, these are nothing but fluxes that are coming in and going out of the shell of a small infinitesimally thickness of delta Z. But as we have seen in the shell mass balance equation, that we need to get the terms of rate of mass of A that is coming in and coming out. So in order to get this term, we need to multiply the flux into the surface area, which is S. So in order to get the rate, we multiply this with the term S, that is the surface area of the shell of thickness delta Z. On getting this, we can now put this into the shell balance equation. Also, before that, another term which we saw was of the rate of production of A. So to get the rate of production, of A, we do rate into S into delta Z. The rate is given to us in the problem as K1 triple prime CA, and S is the surface area of the shell and delta Z is the thickness of the shell. So now the rate of production becomes K1 triple prime CAS into delta Z. Now we write so K is nothing but the first order rate constant. For the chemical decomposition of A. The product K1 triple dash CA, it represents the moles of A consumed per unit moles of A consumed by the reaction per unit volume per unit time. So now getting into the mass balance equation, as we have seen earlier, we might write it again as rate of mass of A in minus rate of mass of A out plus rate of production of A due to homogeneous reaction is equal to 0.